Now we'll look at the cotangent graph. First thing I want you to remember is that cotangent is the reciprocal of tangent. So we already made this table of values for tangent. For cotangent, all we need to do is actually find the reciprocal of those values. Instead of having to recalculate all of them, we can just reciprocal them. Okay, so the tangent of 0 is 0. What is the reciprocal of 0? Well, if we try to do a reciprocal of 0, we end up dividing by 0, which we can't do, so that one would be undefined. The tangent of 30 is 0.6, or remember that was square root of 3 over 3. The reciprocal of that is just plain old square root of 3, which is actually the tangent of 60. So in this case, our 30 and 60 values trade places for our cotangent. So for 30 degrees, the cotangent will be 1.7. 45 degrees, the reciprocal of 1 is 1. 60 degrees, the reciprocal of 1.7 is 0.6. 90 degrees, the reciprocal of undefined is 0. 120 degrees, the reciprocal of negative 1.7 is negative 0.6. 135 degrees, the reciprocal of negative 1 is still negative 1. 150 degrees, the reciprocal of negative 0.6 is negative 1.7. 180 degrees, the reciprocal of 0 is undefined. 210 degrees, the reciprocal of 0.6 is 1.7. And 225 degrees, the reciprocal of positive 1 is positive 1 again. 240 would be 0.6. 270 would take us back to 0, and the pattern will continue to repeat from there. So if we sketch a graph of the cotangent, again I'm making my marks on my graph at every 30 degrees. So 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, 360. That takes us clear around the circle once. Okay, so at 0, it's undefined. So we automatically already have an asymptote right there. It's hard to draw asymptotes on the axis when you're using the same color. Sometimes I like to use colored pencils to make it more obvious where those asymptotes are. Maybe I'll just put all the asymptotes in first. So I know there's one at 0, and I know there's one at 180. And then there's another asymptote at 360, because 360 is the same cotangent values as 0. Now let's put in our intercepts. So we have a 0 at 90 degrees, which is also pi halves. And we have one at 270 degrees, which is 3 pi halves. The next one's going to happen at 5 pi halves, 7 pi halves. See, it actually becomes easier with radians because then you just are dealing with the same denominator for your intervals instead of having to worry about adding bigger and bigger numbers in degrees. Okay, let's go ahead and plug in some of these other points. So 30 degrees is actually up at 1.7. And 45 degrees, which is in between, is at 1 again. And then 60 degrees, which is at 0.6. Then 120 is at negative 0.6. 135 at negative 1. 150 at negative 1.7. If we were to plug in numbers into like a calculator in between here, we would just get numbers that get closer and closer, of course, to those asymptotes. So again, we have a graph similar to an x cubed, except this time it's reflected. So it looks more like a negative x cubed. How is it different from an actual x cubed, though? An x cubed graph, the domain is all real numbers. This one is not, because it has the asymptotes that restrict it from going forever, at least to the left and to the right. Okay, how is this the same as our tangent graph? It's the same basic shape. I think it has the same period, so that means the period of this graph would be pi, just like it is for tangent, because we get 2 repeats in the 2 pi distance around the circle. So in 1 pi, we get 1 of the repeats. That tells us that our period is simply pi. Or if we have that value that changes the period, then we divide by omega to find the period of the graph. Alright, next let's talk about the symmetry. If we turn this upside down, is it going to look the same? Or can we flip it over the x-axis to have it look the same? Well, if our pattern is continuing indefinitely, then that means there will be another one of these over there. So that's not flipping it over the x-axis, because that would be a mirror image along this line, and we would have a line going down this way that looks more like a tangent instead. So this can't be even. If we turn it upside down, does it still look the same? Yes it does. So again, this is another odd function. Okay, where are the asymptotes going to be for this graph? The asymptotes are at 0, 180, 360, every integral value of pi. So we can summarize that by saying k times pi, where k is of course any integer, negative or positive whole number. Next, let's talk about the domain. The domain are the x values, and they exist everywhere that there is an asymptote. Or the domain is the x values which don't exist where there's an asymptote. So we might have a domain that x does not equal, and this should be x equals, this is x does not equal values of k pi. Okay, then our x-intercepts are everywhere that we have the pi half intervals. So the intercepts will be at intervals of pi halves, however, those are actually a distance of pi away from each other. So even though the initial one starts at pi halves, the next one comes a distance of pi later. So we have to add intervals, integral intervals of k times pi to get those other intercepts. So basically a cotangent graph is just a tangent graph that's been reflected and phase shifted. So if I actually wanted cotangent to be written as tangent instead, let's think about what we would need to be able to do that. We would need a reflection, so that would put a negative in there. Okay, then for our tangent graph, this point 0 is here at 0, 0, and this one is at pi halves 0. So not only is the graph reflected, but it's also moved to the right pi halves. So that means that we can change this to a tangent graph by making it x minus pi halves and doing the negative to reflect it. So this tangent graph will be identical to your basic cotangent graph.